Okay, we're continuing with chapter 13 in the statistics textbook. In this video, we're going to go through the third section, which is about the multiplication rule. Now, this isn't the multiplication rule of counting, it's the multiplication rule of probability. But we're going to see, as I mentioned in the previous video, that most of the probability rules we're going to learn are going to have a very simple extension to the counting techniques that we learned. These probability rules are going to almost be trivial when we think about them from the perspective of counting, the perspective of how we can look at any probability problem, no matter what it is, and it all boils down to, you can think about the entire problem as this one fraction bar. Okay, then you have to solve two counting problems, one in the denominator, so the total number of outcomes in general of the event you're looking at, in general, the total number of outcomes, and then in the numerator is the total number of outcomes of what you're deeming to be success or failure or whatever. This here is, the numerator is a subset, is going to naturally be a subset of the outcomes in the denominator, but it's still like you treat it like its own separate counting problem. And so when you think about any probability problem from that perspective, these probability rules, again, they're trivial. So you'll see what I mean as we go through this section. So, okay, it says, this section will show how to figure the chance that two events happen by multiplying probabilities. Okay, so it says a box has 3 tickets colored red, white, and blue. 2 tickets will be drawn at random without replacement. What is the chance of drawing the red ticket and then the white? So without replacement. All right, well, what they're saying here is that the way they go through this problem is they think about it this way. They say, okay, what are the chances of drawing a red ticket first? So the way they're saying to do this is we solve like 2 probability problems first. So we first say, what are the chances of drawing a red ticket? Okay, so we do a probability problem here. Let's put a fraction bar. So what's the total number of let's start with there's 2 counting problems, right? Let's look at the denominator. What's the total number of possible outcomes here? We're just drawing one of these tickets from the box. Well, there's 3, right? 3 possible outcomes. Now, how many outcomes, how many successful outcomes are there? Well, it's just 1. Okay, so there's the probability of drawing a red card. All right, now let's think about what's the probability of then drawing a white card. Well, there's 2 possible outcomes, and one of those is successful. So what they're saying here is that in order to calculate the probability of drawing a red card and then a white card, this is not a conditional probability. If you first choose a red card, then what's the probability of choosing a white card? It's what's the probability of choosing a red card and then choosing a white card. They're saying you just multiply these 2 probabilities to get 1/6. So 1/6 is the probability of choosing a red card and a white card, and then a white card, right? And that's the multiplication rule. It's for probability. It's just saying that if you want to calculate the probability of 2 or more events happening together, like at the same time, like the probability of this event and this event and this event and this event happening, then you just multiply the different probabilities. Okay, but this is we can see how this is a trivial extension of the multiplication rule for counting. So where we can still use the multiplication rule of probability if we want, but in general, we don't have to. In general, we don't have to use any probability rules. In general, you could look at any problem and just strictly do this. Okay, put a fraction bar, and again, now we have to solve 2 counting problems, one in the denominator, one in the numerator. So if we do it this way, from the general perspective, then, okay, let's start in the denominator. What's the total possible outcomes here? So we're looking at the entire problem as a whole. 2 tickets are drawn at random without replacement. What's the chance of drawing the red ticket and then the white? We're not thinking about any probability rules. We're just looking at this from a pure general perspective as a probability problem where we've got this one fraction bar and a counting problem in the denominator and the numerator. So what's the total number of possible outcomes here? okay, well, we've got this box of 3 tickets and we're choosing 2. And order matters. So what's the total number of possibilities here? We could do a red then white ticket, a white then blue, a red then blue, a blue then red. It's 3P2 is what it is. It's just a permutation, right? And that's going to be, so 3 factorial over 1 factorial, that's 6. Okay, now the second counting problem is in the numerator, how many possible successful outcomes are there? So is this just we need to choose a red ticket and a white where order doesn't matter? Well, then that would be 2. But no, order does matter. It's a red ticket, then a white. There's only one outcome there. There's only one way that can happen. And so there's your answer. Now, but how does the multiplication rule for probability work then? Well, all you're doing is, when we did it this way, we're just saying that, like, okay, if we've got one event within a system that can occur successfully M ways, and then there's N total outcomes, and then another event that can occur, it's like this, P successful outcomes and Q total outcomes. And we want to find, and we're thinking about, okay, what's the probability of both these happening at the same time? Well, we're just applying the multiplication rule for counting to the outcomes in the numerator and the outcomes in the denominator to get, so there's N times Q total outcomes. And then there's M times P total successful outcomes, right? That's all you're doing. You're just applying the multiplication. When you multiply probabilities, you're applying the multiplication rule for counting to the events in the numerators and the events in the denominators to get this new total count of total possible events and total possible successful events. That's it. Okay, and so it says, yeah, the chances are 1 in 6, 16 and 2/3%. Of drawing a red ticket than a white ticket. Now it says, for instance, suppose you start with 600 people. About 200 of them will get R on the first draw. Of these 200 people, about 100 will get W on the second draw. So 100 over 600 is 1/6. The people draw the red ticket first, and then the white, and then the white one. In figure 4, the people who draw red and white are at the top left. And so statisticians usually multiply the chances in reverse order. So yeah, I mean, you can multiply the chances however you want, but yeah, the reason 1 out of 3 refers to the first draw and 1 out of 2 to the second. Yeah, that's the way we did it. We said, look, the first draw, here's the probability. The second draw, here's the probability, and then we multiplied them. Now, what they're talking about here is that they're trying to do an illustration of the hypothetical infinite scenario that we've talked about in previous videos, where it can be really helpful to understand the probability problem you're trying to solve, or the exact meaning of the probability you're trying to solve for, by taking a step back and looking at it from that infinite perspective. Hypothetically, it's completely non-realistic. But they try and make it a little bit realistic here by saying that you do this with 600 people. You have this box of 3 tickets. One person comes up and picks 2 tickets from the box, and you note the result. Then they put the tickets back. They shuffle it up. Have another person come do it, and they write the result. Okay, but to me, I mean, it's already not realistic to begin with. Why would you have 600 people picking from a box of 3 tickets? So really, what the whole idea is, we can take a step back and think about this problem, this probability problem, from the infinite perspective. So if we had a trillion people, 100 trillion people, 100 trillion squared people, like this, they would be doing this for years, right? It's really an infinite number of people that did this, right? We shuffled the tickets in the box. One person came up, picked 2 tickets at random, and we noted what the result is. Okay, what's going to happen is, once you do this an infinite number of times, you're going to see that when you take the ratios of the different results to the total number of results, the results where there was a red ticket picked first and then a white ticket picked first are going to be very close to 1 in 6. Not exactly 1 in 6, but extremely close. Like it's going to approach, so 1/6 is what? Okay, so I guess 0.16 repeating. Okay, you would hypothetically, the ratio would be 0.1666666 a bunch of sixes, but it wouldn't repeat forever. It would just repeat for a while because it wouldn't be exactly 1/6, right? And remember, we talked about, because it's if you think about it truly as an infinite number of repetitions here, you might be saying, well, how could it be that close? Because since you did it 100 trillion to the 5th power times, then the actual number of like the red-white outcomes that you're off from being exactly 1/6 might be a billion, right? The amount you need to shift up or down to have exactly 1/6 of the red, what was it? Yeah, red then white outcomes would be like a billion. But because you did it an infinite number of times, a billion doesn't change the ratio that much. This is really a hypothetical. It's like the meaning of infinity. Okay, and what's really useful, another reason why this is really useful to understand the true meaning of probability, even in a realistic scenario, with just like if you went up to a box and you picked the ticket out of the box, what are the two tickets? What are the true chances of you getting a red and a white ticket? Is because you might be thinking, well, what if it's like, doesn't the whole setup and for this infinite scenario need to be perfect, right? There can't be any kind of biases. And yes, that is true, but it's with the infinite scenario, it's very flexible. It's flexible in the sense that, so you could shake up the box and maybe the white ticket gets stuck up against the wall, right? And so then for the upcoming picks, it's really the chance of picking a white ticket is really low, maybe close to 0 because no one's going to feel the wall, right? Well, as long as the ticket, eventually, not too long after you're shaking the box, it comes unstuck, then it's all going to even out anyway because you're doing it an infinite number of times. It would only be the case if the ticket really got jammed in a corner and it was just stuck there for, like a significantly long period of time. Then you would look at the results and see, the white ticket it wasn't what we expected. Something's off here. But the whole infinite perspective, it gives you a lot of flexibility to say, look, the experiment doesn't have to be perfect. Because that in real life, experiments usually aren't perfect, right? Things could sometimes not be ideal, but that doesn't change what the true chances are, okay? So it's the answer here is 1 in 6. It's a 1 in 6 chance of picking a red ticket than a white ticket. Okay, and so now here's the official multiplication rule for probability. The chance that two things will happen equals the chance that the first will happen multiplied by the chance that the second will happen given the first has happened, right? It's not a conditional probability. It's that and criteria, the probability that two things will happen. So the probability that two things will happen kind of at the same time. In the same way, it's like when it comes to the multiplication rule for counting, it's you're counting the number of total outcomes for two events happening at the same time. Okay, so this next example says 2 cards will be dealt off the top of a well-shuffled deck. What is the chance that the first card will be the 7 of clubs and the second card will be the Queen of hearts? So the way we're going to go through these problems, unless it's just trivially simple and quicker to just use the multiplication rule for probability, is we're going to look at them from the big picture perspective. To me, that's going to be significantly more intuitive. So, okay, let's draw a fraction bar here. Now all we need to do is solve 2 separate counting problems. There's no probability rule. So, okay, let's first think about what's the total number of possible outcomes here. 2 cards are dealt off the top of a well-shuffled deck. What is the chance that the first card will be the 7 of clubs and the second card will be the Queen of hearts? So we've got this deck of cards here. Okay, what are the chances that the first card is the 7 of clubs and the second card is the Queen of hearts? Okay, so what's the total number of outcomes in this case? You could have a 7 of clubs, a Queen of hearts. You could have a Queen of hearts, a 7 of clubs. You could have a 7 of diamonds and a Jack of spades, or you could flip those, right? So this is going to be 52 P2. That's the total number of possible outcomes here. Now, what's the total number of possible successful outcomes? Is all we need to do is just pick a 7 of clubs and a Queen of hearts, and as long as we've got those two, it's fine. No, they have to be its first 7 of clubs, second queen of hearts. There's not multiple 7 of clubs and multiple queen of hearts. So there's only one outcome here. Okay, and so that's it. We can look at, so 52, 26, 52. There you go, 1 over 2,652. Now, all they did was, when it came to the probability rule, they had the probability of picking the 7 of clubs first, that's 1 in 52, and they multiplied that by the probability of picking the queen of hearts second, 1 in 51. And so all you're doing there is you're just saying, look, what are the chances of, when it comes to the total number of events, right? The total number of events. When it comes to the denominator, you're saying, look, you pick one card first. There's 52 possible cards. Then another card. There's 51 possible cards. That's how you're getting the total number of outcomes. That's 52P2. And in the numerator, you're saying, okay, you have to pick there's only one possible outcome for the first card that's successful, and there's only one possible outcome for the second card that's successful, so you multiply those two, and you get the total number of successful events. You see? All right, now the next example says, a deck of cards is shuffled and 2 cards are dealt. What is the chance that both are aces? Okay, so, yeah, this is just, okay, so these both need to be aces. So, okay, we do this. We put this fraction bar here. What's the total number of outcomes? It's still going to be the 52P2, the 2652, right? Now, but what about the number of successful outcomes? So both need to be aces. Okay, so now this might be a little confusing for you. The way you want to approach this is it's really a new counting problem. You really, if you're confused, you really want to look at the denominator is a completely separate counting problem than the numerator. It's the same game, but it's completely separate in the sense that you're just thinking about, if you want to think about it this way: if I had to list out all of the possible successful outcomes, how would I list them out? I'm saying that, okay, I could have an ace of hearts, an ace of clubs, or I could pick an ace of clubs and an ace of hearts, right? That's another outcome. Because order doesn't, in terms of me winning, order doesn't matter. In terms of me winning, order doesn't matter. However, I'm still willing to list all of the outcomes where I win, because I'm basing this on, we could have done this problem, since it's a combinations problem in the numerator, we could have done this problem with a combination in the denominator, because we could have said, okay, what's the total number of outcomes where order doesn't matter, because order doesn't matter in this case. And then of all of those, which ones of those is there 2 aces? But since we're doing it where order matters in the denominator, then we want to count all the possibilities where we have 2 aces. So, like, I win if I get an ace of hearts and an ace of clubs, I win. If I have an ace of clubs and an ace of hearts, I also win. So, in that case, we're thinking about, okay, if we're going to list all these out, we've got 4 aces to choose from, okay, and we're choosing 2 where order matters. That's the total number of successful outcomes. So what is 4P2? That's 4 factorial over 2 factorial. That's 4 times 3, 12. Okay, now it says, this next example, it says a coin is tossed twice. What is the chance of a head followed by a tail? And all they did here with the probability or the multiplication rule was just, okay, there's a 4 in 52 chance of choosing an ace first. Then there's a 3 in 51 chance of choosing an ace second, because there's only 3 aces left. Okay, now this next example says a coin is tossed twice. What is the chance of a head followed by a tail? So again, we can say, okay, what's the total number of outcomes here? You're flipping a coin twice. That's a permutation with repetition problem. That's 2 squared, 4. Right? You can get a head or a tail with repetition. So there's 2 outcomes here, 2 outcomes here. Okay, now what's the total number of successful outcomes? Well, that's just there's only one. There's only one way to get a head followed by a tail. And there you go. But they did it with the multiplication rule for probability using It was the first outcome, there's a 1 in 2 chance of getting a head. The second outcome was a 1 in 2 chance of getting a tail. They multiplied those two. But again, to me, this is way more intuitive, especially when you get to more, the multiplication rule for probability, when you've got a really simple problem, it's faster to do it this way. But with a more real world example, it's a bigger problem, then you just do it, you just do the probability problem with just counting, right? Count the number of outcomes in the denominator, then do a separate problem with the number of outcomes in the numerator. Okay. Let's work these exercises now. It says a deck is shuffled and 2 cards are dealt. Find the chance that the second card is a heart given the first card is a heart. And find the chance that the first card is a heart and the second card is a heart. All right, so this is just, these sound similar, but remember this is, they threw in a conditional probability problem here first. This is given the first card is a heart. So the chance that the second card is a heart given the first card is a heart, that's an if-then. So we know this is going to be, you have this deck of cards, right? If the first card is a heart, then what are the chances that the second card is a heart? Well, there's 4 hearts total. So if you chose a heart first, then there's only 3 left, and there's 51 cards to pull from. So 3 and 51. It would be 4 and 51 if you picked the first card wasn't a heart. All right, now find the chance that the first card is a heart and the second card is a heart. This is going to be a lot less probable. Okay, we could say this is so simple, we could just go ahead and use the probability, multiplication rule for probability. So the first card is a heart, there's a 4 in 52 chance. And the second card is a heart, there's a 3 in 51 chance. And you multiply those two. But again, we could have gotten this with that big picture perspective. But this is so kind of trivial here, we can use that multiplication rule for probability. Okay. A die is rolled 3 times. Find the chance that the first roll is an ace, which is the 1. And then find the chance that the first roll is an ace, the second roll is a deuce, and the third roll is a tray. So, okay, let's try and use the big picture perspective. So what's the chance that the first roll is an ace? Well, you roll a dice. What's the total number of outcomes you can get? There's 6. And how many of those are an ace? There's 1, so 1 in 6. Right, but that wasn't a multiplication rule. Now we're going to do the multiplication rule. So find the chance that the first roll is an ace, the second roll is a deuce, and the third roll is a 3. What are the total number of outcomes here? Well, what we're looking at is if you're confused about the total number of outcomes, remember it's really helpful to start just like list out a few of them to see what exactly it is you're counting. So we could have a 1, a 4, and a 3. We could have a 3, a 4, and a 6, right? Now, does order matter? So do we also want to consider if we had a 4, a 1, and a 3? Well, yeah, because order matters here. It's not that we just have 1, 1, 1, 2, and 1, 3 in any order. No, the first roll needs to be an ace, the second roll a deuce, third roll a tray. So this is permutations with repetition. It's 3 cubed. 27. All right, 3 times, or no, I'm sorry, that's not right. It's 6 cubed because there's 6 possible outcomes, 1, 2, 3, 4, 5, 6 with repetition. Because you could roll, the first roll could be an ace, the second roll could be an ace, the third roll could be an ace. So 6 cubed. Okay, now, how many, we do a separate counting problem. How many are successful? Okay, well, is it the case that as long as we get a 1, a 2, and a 3, then that's a success? No, it has to be in this order. And there's only one way you could get a 1, 2, and a 3. So there you go, 1 over 6 cubed. Okay, next problem. A deck is shuffled and 3 cards are dealt. Find the chance that the first card is a king, and then find the chance that the first card is a king, the second card is a queen, and the third card is a jack. So, all right. The first card being a king, there's 4 kings and there's 52 cards. So 4 and 52. Now, the part B, find the chance that the first card is a king, the second is a queen, and the third is a jack. Well, okay, we can think about this. Again, in general, we've got How many possible outcomes here? The order matters. This is going to be 52P3. Now, how many successful outcomes? Okay, this is a little bit different because we have 4 kings, 4 queens, and 4 jacks. So what kind of problem is this? This is just, so we're doing a counting problem in the numerator. This is just a non-permutation or combination. It's a pure product rule problem because each of these we're picking from distinct groups, right? There's 4 possible kings, there's 4 possible queens, and there's 4 possible jacks, 4 cubed. Now you might be saying, well, wait a minute, don't we want to count? Why are they distinct groups? Like, couldn't maybe a jack be here? Well, no. We don't want to count for this distinct counting problem. We don't want to count the outcomes where there's a jack in the middle or a queen here. It's just there's a king here, a queen here, a jack here. So that's it. Now, you could see the parallel to the multiplication rule for probability here by thinking about the first, for pulling a king first is a 4 in 52 chance. Then there's once you've pulled the king, there's 51 cards left. And then once you've pulled the queen, there's 50 cards left. Right, there's 52P3, there's 4 cubed. Okay, the next problem, a die will be rolled 6 times. You have a choice to win $1 if at least one ace shows, to win $1 if an ace shows on all the rolls. Which option offers the best chance of winning, or are they the same? Explain. Okay, well, it's just 2 separate probability problems, right? So to win $1 if at least one ace shows, so the die is rolled 6 times. How many possible outcomes is that? That's 6 to the 6th. That's permutations with repetition. Now, how many successful outcomes are there? Okay, well, at least you've got these 6 rolls of the dice. We can think about it this way. 1, 2, 3, 4, 5. Okay, now I'm going to leave off the 6th because we can put the 1 into any of these slots, right? 1, 2, 3, 4, 5, 6. So, okay, what's the total number of ways you can arrange these 5 outcomes? Okay, this would be a 2, 3, 4, 5, or 6. Well, that's 5 to the 5th. Okay, now, but mixed in there, we can put that, we have 6 slots to put the ace. So 6 choose 1. It's 6 times 5 to the 5th. All right? So 6 times 5 to the 5th, that's 5 to the 5th over 6 to the 5th. Okay? Now, you could win $1 if an ace shows on all the rolls. So it's the same total outcomes, but now if an ace shows on all the rolls, well, that's got to be unlikely. Or wait, no. Hold on, I did that wrong. If at least one ace shows, at least, not just one ace showing. So in that case, we've got, so 6 times 5 to the 5th is 1 ace showing. Now, if 2 aces show, I mean, we don't even need to calculate this. This is just trivial. There's no way this is going to be more probable. Because an ace showing on all the rolls, there's only one chance of that happening. That's going to be 1 over 6 to the 6th. Where here we would do 6 times 5 to the 5th, but then now it would be 6 choose 2 times 5 to the 5th, right? Because you have those 6 slots, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. The 6 slots to put the 2 aces in where order doesn't matter. So it would be 6 choose 2, that's what? Well, let me just do this. It would be 6 choose 1 plus then 6 choose 2 plus then 6 choose, or it would be 5 to the 4th? No, 5 to the 5th. Plus 6 choose 3. So you could like factor out a 5 to the 5th and just do 6 choose 1 plus 6 choose 2. So, but we don't need to do it because there's no way, we know that for part 2 it's just 1. So, and we know for part 1 this is going to be a lot greater than 1. So it would be 1. Okay, someone works example 2A on page 226 this way. For me to win, the queen can't be the first card dealt, 51 chances in 52, and she must be the second card. So the answer is this. Is the multiplication legitimate? And explain. So, okay, what was that example? It was you shuffle a deck and put it down, and now you're going to pull 2 cards, and just what are the chances that the second card is the Queen of Hearts? It doesn't matter what the first card is as long as the second card is the Queen of Hearts. And so it's saying for me to win, the queen can't be the first card dealt. There's 51 chances in 52, and she must be the second card. There's 1 chance in 51. So the answer is this multiplication legitimate? Yeah, absolutely. So yeah, we didn't use the multiplication rule for probability to solve this problem. This was in the conditional probability section. So what they're doing here is they're solving this problem using the multiplication rule, the probability multiplication rule. And I mean, the answer to this question is yes. You just have to analyze the logic that's being used. You're saying, okay, what's the probability that the first card dealt is what you're deeming to be success, what you define to be success? That's just anything but a Queen of Hearts. That's true, right? There's a 51 and 52 chance that in order for you to succeed, you need that first card to not be a Queen of Hearts. Now, what are the chances at that point, if you succeed, that the second card is a Queen of Hearts? It's a 1 in 51 chance. So yeah, the logic is all there. You can use the multiplication rule for probability in any scenario as long as the logic checks out. Okay, a cat o9 blank can be used to punish blank of state, but this is seldom done. Okay, so they're saying that what's the chance a cat o9 tails is used to punish heads of state? If a coin is tossed twice to fill in the blanks, what's the chance of the coin getting it right? So, okay, you toss a coin twice. There's 4 possible outcomes. Okay, and now what's the chance of you need to get a tails, then a heads, and that's in that order, 1 in 4. Okay, a coin is tossed 3 times. What is the chance of getting 3 heads? All right, so you've got, there's, the total outcomes is what? 2 cubed, or that would be 8, and 3 heads. There's only one way to get 3 heads. What's the chance of getting 3 heads? So there's 8 outcomes. Now, how many of those have 3 heads? Well, you just say, so you could do, let's see, 1, 2, 3, or no, you could do it like this. You've got these 2 heads here, or no, how many times? Oh, okay, wait a minute. Chance of getting 3 heads, the chance of not getting 3 heads. Well, okay, this is just it's that complement rule. It's going to be 7 and 8, right? It's the opposite of part A. Okay, what is the chance of getting at least 1 tail? So in this case, it's still going to be 8 outcomes, right? Now, you've got, let's see, to get at least 1 tail, so you've got these 3 rolls. Okay, at least 1 tail. So okay, what's the probability of getting 1 tail? Well, okay, it's going to be, you have like a head, tails, heads. It's just you put the tail, it's 3, right? It's 3. Now, okay, so that's 3 plus, what about getting 2 tails? Tails, tails, heads. So you could put the heads in any slot. That's another 3. Now, all tails, it's 1. 3, 6, so 7. Now, the probability of getting at least 1 head is also going to be 7 and 8. It's just the same thing.